Okay, so yeah, let's get started. So, okay, so let me check the camera to see. Okay, yeah, sounds good. Okay, uh, okay. I think wait. Um, okay, so where's the chalk? Okay, so here. Okay. Okay, so I think that last time I'm left off with the case where okay, so yeah, so remember yeah, it's like the uh, yeah, we are trying to show the converse direction, right? So we are trying to show the converse direction, and okay. Okay, so okay, I think that I left out the page to show that. So finally, uh, uh, okay, so yeah, finally, uh, so so we may choose a connected neighborhood u naught of y naught with u0, which is contained in this v intersect um, those small r in this gamma 1 vr intersect with r inverse of wr. Okay, so yeah. Yeah, so okay, so let's see whether this is true. So we may choose a connected neighborhood u naught of y naught with u naught is contained in v set. So this v is what? This v is like the yeah. So this v is like the relatively compact neighborhood of y naught in this f tilde, right? Yeah, because this f tilde is like a relatively compact, right? Yeah. So this f tilde is locally compact. So therefore, we can choose the relatively compact neighborhood E of y naught. Yeah. inside this yeah, so that it also it also has the property that this gamma of gamma of v intersect v is gamma of v intersect v is not empty for finally many finally any for it's not empty finally element. Okay, it's not empty for finally many element. Okay. Yeah. Okay. Okay. Wait, it's not empty for. Yeah. Okay. 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 So let's see why we can choose a connected neighborhood of y naught with that. Oh, okay, I see. So yeah, because this space X is locally similarly connected, right? This space X tutor. Yeah, and then it's locally similarly connected. And also it's locally similarly connected. And also this I want to say that this set is open. Oh wait, shoot! I think so this should be v. Okay, this okay. So this u0 is contained in this v intersection of gamma in this gamma 1 of v gamma intersect that one. Yeah. Oh, this is true. Okay. So since this x tutor is locally similarly connected, and then this v gamma, I want to say and so since and also this v of r, yeah, v of r, small r, and r inverse of wr are both so this wr is open, right? And then this r is dash transformation, right? So dash transformation means that it's a homomorphism, right? Yeah, and then so okay, yeah. So wait, why I'm confused? Yeah. So okay. Yeah. Okay. Yeah. So then, therefore, yeah. So therefore, this is open. Okay. And then you take finally intersection. It's also open. So this implies that. Yeah, so then you intersect this open set.
Wait, hold on. If you have a set that is relatively compact, does this implies that
Oh, okay. Yeah, so this V is a relatively compact neighborhood. So this V is open. Okay.
hold on, let me check why we can choose such relatively compact. Oh, okay, yeah.
Okay. Okay. Yeah. Okay, so these are all open. Okay. So and then so we may choose a connected neighborhood U0 of Y. Okay.
So okay. So since the space is locally connected, for every point PS, okay.
Okay, yeah. So yeah, so this is true by definition. Okay. So since it's open and then because this set is open. Okay. Okay, yeah, it's locally simply connected. So therefore, so these are open. So this implies that and then because this is open, right? So here this implies that this set we intersect this intersection of R in this R gamma 1 of VR intersect this R inverse of WR is open. So therefore, because this X is locally simply connected, so yeah. So since it's locally simply connected, we can pick the connected neighborhood of this set. Okay. So we can pick take this U naught as a subset of this V intersect the intersection.
So then
okay, so yeah, so connect it, okay.
Okay, yeah, so I checked for some definitions. Okay, sure, yeah. Okay, okay, so here, what I want to, so what's next? Alright, so what's next? Okay, so now,
okay, so then that is U to be defined as this gamma of the gamma of this U naught.
then we get,
Okay, so we get this big gamma inverse of this U is equal to this gamma. So the Dirac transformation group acting on this U naught, which is the same thing as the union of this small r in this gamma of this r of U naught. Okay. Yeah, so okay, so let's see the first inequality. So okay, I think this is true by okay, so let's show this. So why you have this gamma inverse of U, okay. Is gamma acting on, yeah, is gamma acting on this U naught. Is gamma acting on this U naught. Let me see. Yeah, so this is the, yeah, so this is wait. Gamma acting on the U naught. Okay, so yeah, I think this is the definition of gamma acting on U naught. Yeah. Oh, okay. Because okay, let's show that. So so if you take any okay, so let's show that this okay, so let's say that let's say if you take any x, maybe because it's in the common space, right? Let's take any x tilde in this case of U. So So y, this is in O. Okay, so okay. So if U is equal to this gamma of U naught, right? Um, okay. So I this U naught is in that. So this U naught is connected. So therefore, let me think. If U is in gamma of U naught. This U is just gamma of U naught, right? But the thing is that we don't know whether can we pick a point. Can we pick a point in this U naught, right? So can we pick a point in this U naught that we can use this as our base point? Okay, yeah. So okay. Since this yeah, so since you have U is equal to this gamma of U naught, so there is a maybe let's call it x to the prime in this U naught, or x to the 0, okay, x to the naught in this U naught, such that gamma of x to the naught is equal to gamma of x to the, okay, right? Because yeah, okay, and then let's see what happened. Then you have that then what? Let's see why it's, oh wait. Okay, so the idea is that we can use this x naught as our base point, right? So wait, is gamma a covering space projection? haven't shown that yet. Okay. So yeah, we can use that. We can use the covering space property. Because we haven't shown that this gamma is a covering yet. Okay, so what do you want me to show now? Okay, so what is this gamma? Okay, so this gamma is the okay. Oh, okay. Okay. So this gamma is a group of okay. Okay. Yeah. So since so this gamma acts
freely on this S, right? If for every element if every element are small on this gamma with small non-triviality at every point.
now equal to identity. No. Let me think. So okay, so this U naught is in. So we haven't used the property that this U naught is in this set, right? We intersect this R in. Okay. Gamma 1 such that. Okay, so let's see what did we do? Okay, what did we do? Or what have we established? So we show that this gamma is open mapping, right? So we show that this is an open mapping. So we show that this gamma is an open mapping.
And then we also show that
And then we define this final set, right?
we define the because we know that this group acts properly discontinuously on X. So wait, okay. because we know that it's x property discontinuities on this x, on this x tilde, sorry.
So we take a point, right? So yeah, remember we pick this point right now to be,
Wait, what is the point right now? Hold on, what is the, yeah, so we pick a point x naught, right, as our base one in x, okay. So and then we pick this y naught to be one of the element in the fiber of this x naught, right?
so basically,
So suppose that this is the x. Yeah. Oh, okay. Okay. Okay, so this x is okay. So this x is the quotient space, right? So this x is the quotient space of this. Yeah, it's like the x tilde quotient by the relation of this gamma. Okay.
so the points are related by, like, if its points are related by the relation that one is the, if x is equal to y, right? So x, yeah, so these 2 points are related if only if the, yeah, one point is the image of another point under some element in this gamma. Yeah, so this is like the relation between these two, right? And then so we pick a point, let's say x naught here. Okay, so then, so this is a quotient map. Okay, so this gamma is a quotient map, and then this is the upper stairs. So maybe really I should write is that I should write, instead of writing x tilde, I should write the equivalent class under the gamma. Okay. And then, so upstairs, okay. Okay, upstairs, what happened? So upstairs, there might be some points, let's say. So upstairs, there are the points that's related to this x naught tilde, right? So they are the points where, after some, okay. Oh, okay. Yeah, so you can think of the points for here. So this is x naught, definitely here, because you have the wait. Do you have the identity element being contained in this? So you may not have the identity element being contained in this subgroup. Wait. Oh, since this gamma is a subgroup, so it must have the identity element. Okay, so because it's a subgroup. Yes. So therefore this x naught must be contained in the pre-image. And then, okay, so the fibers are exactly this x naught together with
Okay, so the fibers. So if you take the gamma inverse of this, oh, okay, I think I think we're done, right? Because yeah, think of this as just a point, right? So think of this one as just a point, right? So if you think of this as just a point, then what happens if you take the preimage of that point? So if you take the preimage of that point, then it just give you this one, right? It just like by definition, right? It's all the point that's being related by gamma to this point. What are the point that's related by gamma? Basically, they are all like the set of all this relation, right? Where this R is in gamma. Okay. So then, yeah. So then, yeah. So if you take the gamma inverse out of U, right? So basically, wait, what is U now? Okay. Okay. So, if you take any element here, oh, okay. Yeah, so since this x naught tilde is in U naught, right? Did I say that it's in U naught? Yeah, I can specify it to be U naught, right? I can specify it to be the point in U naught. So therefore, you just, yeah, you just do the transformation on this x naught tilde, and then you will get everything. Okay. Yeah, I think. Wait. So for this, yeah. Okay, so, yeah, so if you take any point, right? Because of this property, yeah, because, so basically if you take any point, x tilde, then you know that, yeah, this x tilde is in one of these, yeah, so you have x tilde being contained in that, okay, and then if you take any, yeah, any u now, okay, yeah, I think this is true, okay, this is true, okay, all right, so yeah, yeah, so yeah, so basically as long as you have this, right, so this holds for like a single point, then you can basically show that if you take any point, let's say here, right, and then you do like the gamma x is in U, and then this gamma x tilde basically is just this one quotient by this relation, the equivalence class of this relation, right? Where this point is, and then for this point, you can always pick the, yeah, you can always pick the corresponding point, right? You can always pick the corresponding point in this U now, right? Because this point is in U, right? Yeah, you can always pick the corresponding point in this U now, and then after that, they are on the same fiber. Yeah, they are on the same fiber. So therefore,
since they are on the same fiber, then you apply this to this point on this u0, and then you get that. Okay, so this is how you do like the forward direction, and for the backward direction, what you do is that pick any point in the disjoint union. So then you take what? You take the projection, right? You take the projection, and then let's see what happens if you take the projection. So for the backward direction, what you do is that if you take any, let's say x tilde is in that. Wait. What do I want to say? Oh, okay, yeah. Okay. So then you look at this one, right? You look at this. Okay. So once you look at this, okay. So yeah. So this implies that this x tilde is equal to some small r of let's say x naught tilde, where x naught tilde is in this u0, small r is in this gamma, right? And then this implies what? This implies okay, yeah. So this implies that this is equal to this. Okay, because they are related by that. And then what do I want to show? Okay, I want to show that basically it's the same thing as I show that. Oh, yeah, right? Because this one is in U, right? This x naught is in u0, so right. So let me see. So okay. So gamma inverse of u, right? Okay, I want to show that. So wait. Okay, I want to show that this guy lies in. Okay, so why this guy lies in. Okay, gamma inverse of u. So okay. So wait, I'm confused. I want to show that this x tilde. So this is the x tilde, right? So this is the x tilde, and then okay. So gamma of gamma of x tilde is equal to this, and then equal to that, and then which is equal to where y is lies in u. Okay, I want to say that this lies in u, right? So why this lies in u? yeah, this is less than u because so which is this is less than u, exactly. Okay, I think this is the proof. Okay.
All right, so okay,
So now let's
so now
so this one is being shown here.
and then okay,
So and hence so remember so basically our goal is to show that this gamma is a evenly covered set. So our goal is to show that this this u now is this u is even covered. Okay, this is our goal. Okay, so hence, so in order to show that this u is evenly covered by this gamma, so it suffices to show. Okay, so hence to show that this u is evenly covered by gamma, it suffices to show that so namely we we'll have that, right? Namely we show that. Okay, so to show that it's evenly covered